So our first task is to set the table for what the derivatives of a function of several variables should actually be telling us about that function. And so the preview activity in this section sort of calls back to this function of two variables that is a monthly payment formula that relates to the principal, so the amount of money that I'm borrowing on a loan. Call that actually, the principal isn't a part of this. So the principal is fixed here. It's a $18,000 loan. And so the two variables here are the interest rate that we get on the loan as an annual percentage rate, and then the length of term. So how many years do we want to have to repay this loan? And so this function of two variables, R and T, give us the monthly payment for an $18,000 loan related to the interest rate R and the number of years of term, which is T. And so this is a formula for that monthly payment. And so what this preview is having us do is kind of think about what it should mean to take some traces of the graph of this function. In other words, when we take a trace, remember we're intersecting the graph of a function with a vertical plane. And a vertical plane in xyz space is just taking either x or y and setting it equal to a constant. So all of the x's are the same along one plane, or all of the y's are the same along the other plane with which we intersect. And so when we do that, we get a slice, a trace, out of the two-dimensional surface, and that trace is just a curve. And so we can ask, what are the slopes of tangent lines to that curve? And that's going to hopefully give us some idea of what a derivative for a function of several variables ought to look like. So the first question in this preview activity is just, what would the monthly payment be for 3% loan with a 4-year term and $18,000 principal? And so for that, we would just evaluate this function for r equals 0.03 and for t equals 4. And that's going to give us a monthly payment of $398.42. So that's no calculus involved there. That's just evaluate this function of several variables at the point in question. So now the next part is where we start taking traces, slices of the graph in vertical planes. And we do that by saying things like, suppose that the interest rate is guaranteed to be 3%. So suppose that we don't let the interest rate vary. We just let the interest rate be 3%. And look at how the monthly payment depends on the length of term only. So in other words, if the lender is coming back to me, I'm trying to borrow $18,000 to buy a car, which is about what I had to borrow to buy my last car, last time I bought a Ford Focus. So when I did that, when I was applying for that loan, right, they might say, well, we can give you a 3% interest rate, but you're going to have to choose, what the length of term, how many years of repayment do you want on this? And so then the monthly payment is going to depend on that length of term. So M is going to depend on T only if we replace R, the interest rate, with a constant, 0.03. So the question here asks us to do that calculation, so replace R by this constant, and get, therefore, a single variable function. We can look at the graph of that single variable function, and it should tell us something about the multivariable function. So if I let R be the constant, 0.03, then I would just evaluate this function at R equals 0.03, and the only variable that would remain is the variable t. So what we accomplish is we reduce a function of several variables down into a function of a single variable. And the graph of that function of a single variable looks something like this. So here is the 4-year term, interest rate 3%, monthly payment $398.42. But now t is my independent variable. So my length of term, my repayment, is allowed to vary, but my interest rate is not. And so naturally, if I want to take a longer payment term to pay back my car loan, then my monthly payment, how much I have to pay each month, is going to go down. Whereas if I want to pay off the loan more quickly, then my monthly payment is going to have to go up. And so this shows just that dependence without letting the interest rate change and only letting the length of term, only letting t vary. And so now that we have a single variable function, we can do single variable calculus on that function, which is, of course, why single variable calculus is a prerequisite for our course, right? We can just take a regular old derivative and find an instantaneous rate of change of this function at the point t equals 4. And if I do that, this is a really nasty derivative, by the way. This is one where I kind of stopped in my tracks. I'm like, oh, that's kind of nasty, right? If you look at this function, it has like, let's see, it's got a 1.0025 to the minus 12t down here in the denominator. So we end up needing to use either a quotient rule or a chain rule, and then needing to remember what the derivative of a exponential function with a base that's not e is equal to. So you do this big ugly calculation, then you evaluate at t equals 4, and you get this number, negative 93.75. So one of the most important things to remember anytime we're talking about derivatives, regardless of which context that we meet derivatives in, derivative always tells us a rate of change. It's what is the proportional rate of change of the output from my function per unit change in the input. So when I change the input by a little tiny amount, by what multiple of that tiny amount does the output change? So that's how we're thinking of the meaning of a derivative. And so the units on the derivative are always going to be the units of the output of my function divided by the units of the input of my function. So this function spits out a monthly payment, so the units of its output are dollars. But it takes in t, and t has units of years. And so the units of this derivative are going to be dollars in the numerator divided by years in the denominator. And so the units are going to be dollars per year. So if I want to interpret the meaning of this instantaneous rate of change, it's the slope of this tangent line to the graph of my trace, my single variable trace of this multivariable function. And that number, negative 93.75, is the slope of that tangent line, measured in dollars per year. So I might say that what this number tells me is that compared to a loan with a 3% interest rate, which is not varying, and with a repayment term of 4 years, which has a monthly payment of $398.42, if I increase my time, my term of payment of my loan, so if I increase t, then my monthly payment is going to decrease at a rate of $93.75 per each additional year that I increase my term. Right? So it tells me that rate of change at that point. Right? So really what this is doing, right, is it's taking my multivariable graph, it's taking a trace of it, so a slice of it through a vertical plane, and then it's taking a tangent line to that trace. Now you might imagine that a tangent line to the trace, the single variable trace of my graph, is also going to end up being a tangent line to the entire graph, which is my surface in 3 dimensions. That's a little teaser of where we're going to be going with this ultimately. So if we could somehow resituate this picture back inside of the 3-dimensional graph, then this green tangent line that we drew to the trace would become a tangent line to the surface, which is the graph of my multivariable function in 3 dimensions. And its rate of change would still mean the same thing. It would tell me that the monthly payment is going to decrease by 93.75% per each additional year that I increase the term, starting from a 4-year term. So if I do all of that slicing with a constant interest rate, what I get is a multivariable function, a monthly payment that depends only on the repayment term. It depends only on t. And so if I did that in one way, I could also do it in the other way. If instead I say, well, let's imagine that my 4-year term is fixed, so I'm not going to change that. And maybe I'm shopping around to different banks and different lenders, and I know that I want a 4-year loan of $18,000, but I'm shopping around to find the best interest rate. And I know that as the interest rate goes down, my monthly payment is probably going to go down, and vice versa, right? And so the question is, how sensitive is that monthly payment to changes in the interest rate, as opposed to changes in the length of term? So here we replace t, the length of term, with a constant, 4 years, and then we study the dependence on r, the interest rate. So now we're taking a slice in another vertical plane that's perpendicular to the previous vertical plane that we took a slice with respect to. And so setting r equal to 0.03, we now get this new single variable function that depends only on, well, again, we're calling the thing t here, which is probably an unfortunate variable to use here, because actually the meaning of this single variable here is r. It's the interest rate. And so it depends only on the interest rate, which appears now in these 2 different places in the formula. And so again, I can take the derivative of this, which is even nastier than the previous derivative, because you end up needing a quotient rule to do this one, as well as a chain rule in the process. So you do some nasty derivative. You evaluate this at our original interest rate of 3%, 0.03 for r, and you get a slope, 795.54, which is a slope of a tangent line to that slice of my graph at the point where the interest rate was 3%, the length of term was 4 years, and therefore the monthly payment was $398.42. And And so that, again, that number, 795.54, tells me that compared to my original loan with a 3% interest rate and a 4-year term, if I increase my interest rate, then my monthly payment is going to increase at a rate of $795.54 additional dollars per every increase of 1 in my interest rate variable. But because my interest rate is measured in percent, right? That increase of 1 would really be a 100 percentage point increase, which is why this number, 795.54, sounds so big, right? If I jack up the interest rate by 100 percentage points, then we would expect a pretty drastic increase in the monthly payment. And so, as I mentioned in a comment over here, probably the easier way to think about this is just to scale both of those numbers down by a factor of 100 and say really what we're meaning here is that every 1 percentage point increase in my interest rate will be associated with a $7.95 increase in the monthly payment. So just scale them both down by a factor of 100 to get a little bit, that's probably the interpretation that you would want to tell a client of your bank or something like that as far as the meaning of this goes. So what this activity has done for us is just sort of set the stage for what we're talking about, right? We take a multivariable function, so it depends on more than one quantity. And we take a slice of its graph by holding one of its variables constant and letting only the other one vary. And when I do that, I get a single variable function where only one of those variables from my original function is allowed to change. And then I can use the tools of single variable calculus to compute derivatives, which have the same meaning, the slopes of tangent lines, the instantaneous rates of change, etc., as they did in single variable calculus.